In this problem, we're told that a fair die is rolled repeatedly until the running total is at least 100. So the first roll might reveal a 1, second roll a 1, third roll a 3, etc. And the running total after the first roll would be a 1, after the second roll would be a 2, after the third roll would be a 5, and so on. And this process stops when the running total is at least 100. And we're asked to find the most likely running total after the process has finished. So one thing to note is the maximum running total is 105. And the reason the max total can't be 106 is because the largest value that a die can roll is a 6, which would imply that the running total on the running total before the last roll would have to have been 100. Well, if the last roll had revealed a 5, that would imply the running total before the last roll would have to have been 101, and so on. But the moment the running total lands on the running total is 100, the process terminates. So there's no way to reach a running total of 106. So the max total is 105. So we're going to make a couple definitions here. X sub I will be the event that the die lands on value I, and S sub I comma j is going to be the event that after I rolls, the total is j, and then the number of rolls the process takes to terminate we're going to denote by L. So lowercase l is going to be number of rolls until the process terminates, till termination. So what we are asked to compare is the probability that the running total after L rolls is 100. We need to compare this to the probability that the running total after L rolls is 101, is 102, 103, 104, and 105. So we want to see which of these possible maximum running totals are the most likely. So to do this, we're going to use law of total probability, and we're going to rewrite this expression as the probability that the running total after the L minus first roll was 900 times the probability that the last roll reveals a 1, given that the running total after the L minus 1 rolls was 99, plus the probability that the running total after the L minus 1 rolls is 98 times the probability that the last roll reveals a 2, given that the running total was a 98, plus plus the probability that the running total after the L minus 1 rolls was 94, times the probability that the last roll reveals a 6, given that the running total up to that point was 94. Now here we have the probability that the running total after L minus 1 rolls is 99, and the probability that we have a 2 on the last roll, given that the running total up to that point was a 99, plus we're going to skip writing all these terms, and the last term will be the probability that the running total after L minus 1 rolls was 95, times the probability that the last roll was a 6, given that the running total up to that point was a 95. Here we have the probability that the running total up to that point is a 99 times the probability that a 3 is rolled, given that the running total up to that point was 99, plus ... plus the probability that the running total up to that point was 96 times the probability that a 6 was rolled, given that the running total up to that point was 96. So we can see, without writing these three explicitly, the last three probabilities explicitly, we can see a pattern here. And the pattern is the following. So the probability that the running total after the process stops is 100 equals the sum from I equals 94 to 99. The probability that the running total up to that point, the probability that the running point up to that point was I, times the probability that the last roll was 100 minus I, given that the running total up to that point was I. Now, the probability of rolling any particular value is independent of what the running total up to that point is. And the probability of rolling any particular value is 1/6. So this becomes 1/6 times the sum from I equals 94 to 99. The probability that the running total up to that point was I. Now let's look at the next value here. So the probability that the running total in the end is 101. So here we said the first term, the very first term, again, the very first term is we roll a 2 and the running total up to that point is 99, and the last term is the running total is 95 and we roll a 6. So we start the running total with 95 and we're again going to go to 99. The probability that the running total up to that point was I times the probability of rolling 100 minus I, given that the running total up to that point was I. So we see that this is exactly the same computation as above. This is 1/6 times the sum from 95 to 99, the probability that the running total up to that point is I. What about for the third probability here? What about the probability that the running total in the end is 102? So we see that the running total index should start from 96 and is going to go up to 99. So the probability that the running total in the end is 102 equals the sum. Our index is going to start from 96 and going to go to 99. And again, we have the probability that the running total up to this point was I times the probability that the die lands on 100 minus I, given that the running total up to this point was I. And again, we see that this is equal to 1/6 times the sum I from 96 to 99. The probability of that the running total up to that point is equal to I. So we can see that these values here, looking at these three values here, we can see that they're decreasing. And so the most likely one of these terms is the probability that the running total when the process terminates is 100.